Okay, so we continue our discussion on DFT. So in the last lecture we discussed the symmetry relationships for DFT and introduced the concept behind discrete Fourier transform. So what is the concept? There are n pieces of information, okay, capital N number of pieces of information in the time domain as well as in the frequency domain. Okay, so and this n pieces of information should be adequate for any signal. Okay, so these n pieces of information are usually obtained by sampling the Dtft. Okay, so you take Dtft, discrete time Fourier transform, it is denoted by x of e to the j omega. You sample n number of samples, you will get a x of k. Okay, so these n pieces of information are usually obtained by sampling the Dtft at capital N number of points, and this capital N number of points are evenly spaced. Okay, evenly spaced means what? Uniform sampling. So we employed uniform sampling. We also stated the formulas for DFT and IDFT and emphasized that one follows from the other. The two are not independent of each other. Okay, so the DFT and IDFT are not independent of each other. One follows from the other. Okay, they are one-to-one transformations, and we sketched the proof of inverse discrete Fourier transform, and we gave some examples like the DFT of del of n, then del of n minus m, and cos of 2 pi r n divided by capital N. Okay, then we said that DFT is useful and important because of FFT, which itself is not a new transformation, it is an algorithm for computation of discrete Fourier transform. Okay, then we showed how from the n samples in the frequency domain x of k, where k is equal to 0, 1 up to n minus 1, how to find the total spectrum, the gross spectrum x of e to the j omega, how to move from DFT to Dtft. We know how to move from DTF to DFT through this process, right? Through the process of sampling we can move from DTFT to DFT, but we need to know how to move from DFT to DTFT. So that process we said something called interpolation. Okay, and that is obtained by the so called interpolation. Okay, and the interpolation formula does not look very nice, but it can be programmed, and then you can rapidly compute the in between samples of DFT using that formula. And now let's move on to the relationship between x of k and relationships between x of n, relationships between DFT and IDFT in more detailed manner. Okay, how it can be expressed or represented in a compact way, and how you can compute using your computer. Now the DFT is given by x of small k is equal to summation of x of n e to the let me write in the compact form, capital W suffix n kn. Okay, where k is equal to 0, 1, 2 up to n minus 1. You see this x of k contains capital N number of equations. When you substitute k is equal to 0, you will get a x of 0, you will get one equation. Substitute k is equal to 1, you will get another equation. K is equal to 2, you will get another equation. right? If you expand, then this guy becomes x of 0 wn0 plus x of 1 wn0 plus x of 2 wn0 plus keep on goes. And here x of 0 wn0 plus x of 1 wn1 plus x of 2 wn2 and so on and so forth. Similarly, x of 2 you can write, then x of n minus 1 is equal to x of 0 wn0 plus x of 1 wn to the n minus 1 plus dot dot dot. How many equations do I have here? 1, 2 up to all the way n minus 1. So I have capital N number of equations. These equations are linear equations. Okay, I have k number of equations and these equations are linear equations. So this is a compact way of writing the same n equations. So in the compact form we can write these n equations. Okay, since it has n linear equations, we can also write in the matrix form. Okay, so I can take the help of matrix and I can write it. So this matrix form is another way of writing x of k. Matrix is also a compact way of writing a set of n number of equations. See, this n number of equations, x of 0, x of 1, x of 2 up to x of n minus 1, in this form you can write, or you can write in the matrix form as follows: x of 0, x of 1 dot 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 x of n minus 1, and here in the matrix form you can write 1 comma 1 comma dot 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 1, and here 1 wn power 1 wn square, then wn to the n minus 1 dot 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 dot, here this is 1 wn to the n minus 1 wn to the n minus 1 multiplied by 2 dot 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 wn n minus 1 the whole square multiplied by the samples x of 0, x of 1, x of n minus 1. So the matrix form is also a compact way of representing x of k. Now look at this matrix. This matrix is a square matrix, okay, of dimension n, and the square matrix is represented by the symbol d suffix n, and here this n indicates dimension. Okay, so this n indicates dimension, and here dimension of this matrix is n by n, and this one capital X, it's a column vector. This column vector I can represent like this, is equal to d suffix n, and this is also a column vector but small x bar like that. So this is the compact way of writing the DFT in another way. And it is obvious that while the direct DFT can be written in the matrix form, and similarly the inverse DFT, if you look at the formula inverse DFT, what is inverse DFT? X of n is equal to 1 over n summation of k is equal to 0 to capital N minus 1 x of k wn kn, and here minus kn. If we expand this guy also, it has also x of 0, x of 1, x of 2 and so on dot 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 up to x of n minus 1. In the right hand side also you have capital X of 0 times wn power 0, like everything is same, only this small x and capital X are interchanged. Instead of plus you have minus here, that's all. So that is a difference between DFT and IDFT. So interchange these two guys. So in the left hand side, instead of capital X I have small x bar. Okay, again the same dn, because everywhere this wn is multiplied by the same fashion. So dn, and instead of the small x, let me put a capital X bar. But here, if you look at the formula, here I have minus symbol. So this is nothing but inverse matrix, inverse of this square matrix. So therefore I put inverse here. Okay, the only change is, that is, if you write the inverse discrete Fourier transform formula in this form, then the only change is the scaling factor 1 by n, 1 by capital N, that scaling factor comes, and instead of, if you look at here, instead of Wn power kn, here we have Wn power minus kn, that's all. That is the only difference. See, look at the minus symbol here, and this multiplication factor. So therefore, let me put 1 by capital N here, and because of this minus, I took the inverse of operation. Therefore, x bar is equal to 1 by n, the square matrix dn, you take inverse of that, and x bar. So this is IDFT. Okay, so there are two difference. One is multiplying by 1 by n, and the second point is e to the minus j 2 pi by capital N times kn becomes e to the plus j 2, this is in DFT multiplication, and here e to the plus j 2 pi by n kn, that's all. So how do you move from this guy to that guy? You take the conjugate of that. Therefore dn becomes dn complex conjugate. Therefore it follows that. So why did I put inverse here? See, from this how can I get back this equation? You pre-multiply by d inverse on both sides. So you take this equation, d inverse x bar is equal to d inverse dn, d suffix n, and small x bar. I am sorry. 1 second, let me write it formally. See, originally we had x bar is equal to dn and small x. Now pre-multiply by dn inverse on both sides. dn inverse x bar is equal to dn inverse dn times x. dn inverse times dn becomes identity matrix in. Identity matrix times x bar is equal to dn inverse x bar. So this implies x bar is equal to dn inverse times capital X bar. This is through matrix operation. But conceptually what you can say is this e to the minus j, if you take the two formulas, your x of k is equal to summation of x of n e to the minus j 2 pi by capital N kn. Your x of n is equal to 1 by capital N summation of x of k e to the plus j 2 pi by n kn, and here there is a minus symbol and no minus symbol. So how do you move from this side to this guy? You take complex conjugate. Okay, so in this you have x bar on the left hand side, in the right hand side you have dn, then small x bar, and from this what do you write? X bar, which is 1 by n, and this is my dn, right? So it is a complex conjugate of this guy, therefore dn complex conjugate of capital X bar. And compare this guy and this guy, both must be same. Okay, both must be equal. Therefore d inverse is same as dn complex conjugate. So no need to take the inverse matrix, you simply take the complex conjugate of every element in the matrix. Therefore it follows that dn star inverse is nothing but dn complex conjugate. So if you know d suffix n, that is the only thing you have to know, then you can do either DFT or inverse discrete Fourier transform IDFT. In other words, the same algorithm which is used for computing DFT can also be used for computing inverse discrete Fourier transform, and this is one of the versatility of the DFT operation. Okay, same algorithm can be used to compute both DFT and IDFT. Okay, so in DTFT, x of e to the j omega is equal to summation of x of n e to the minus j omega n. But inverse discrete time Fourier transform, what is the formula? X of n is equal to integral of minus pi to plus pi x of e to the j omega e to the j omega n d omega, and here you have summation and here you have integration. So you cannot use the same algorithm or same thing for both DTFT and IDTFT. But in DFTs and IDFTs, you can use the same algorithm. That is a versatility. In fact, you can use a digital computer to perform this continuous integration, but the algorithms are different because here integration and here summation. But in DFT and IDFT, algorithms are the same. The only thing you have to change is introduce a scaling factor. Where is that scaling factor? This one. Introduce only the scaling factor 1 by n and change the power of Wn to Wn my inverse. That is, take complex conjugate. That's all. Okay, so straight away you can calculate the IDFT using the algorithm. So this matrix representation is very important. Although it looks like a mathematical representation only, we showed that x bar, capital X bar, is simply dn times small x bar, where dn is an n by n square matrix. X bar is equal to dn times x bar. This is a square matrix. And similarly, the IDFT can be written, this is DFT, and IDFT, how do you find out? IDFT, small x bar is equal to 1 by n dn complex conjugate and x bar. The matrix representation we will demonstrate. Okay, we have demonstrated the matrix representation, and this is very much useful. Okay, and one point that I wish to emphasize here is that if x of k, capital X of k is for capital X of k, if n number of points are given and you wanted a denser representation, I mean you want in between samples, you can do it by a process called interpolation. Okay, you do interpolation and you can get the points in between 0 to n minus 1. Okay, so using DFT, suppose your x of n exists, the time domain sequence exists from 0 to n minus 1. Okay, and you wish to compute from this x of k, that is n point DFT, where k goes from 0 to n minus 1. So this is the usual DFT. No problem, you can use a finite sum formula and you can find out. So x of n is from 0 to n minus 1 and x of k also from 0 to n minus 1. This is usual DFT. Suppose you want to compute x of k not at 2 pi by capital N intervals, but at smaller intervals. That's what you mean by interpolation. See, the given sequence is 0 to n minus 1, let us say 0 to 127. That means 128 points, 128 point DFT. But you would like to compute 0 to 255. How will you do that? So here the n value is 128 and here the n value is 256. Let me call this as capital M. So instead of doing n point DFT, I would like to compute m point DFT, where m is greater than capital N. How will you do that? If you take n point DFT, then you divide 2 pi by 128. If you take m point DFT, then 2 pi divided by capital M, which is 2 pi divided by 256. But in the given sequence, in the time domain sequence, I have only 128 sample points. How can I do that? And here M is much greater than capital N. Okay, and you may wish to compute maybe sometimes capital M is equal to 1024 point DFTs. Okay, capital M can be 1024 or 2048 or whatever it is. Then it will be a very dense representation. If you take 1024, it gives you dense representation, and the envelope will represent almost accurately as good as x of e to the j omega. What you can do is, alternate is sometimes preferable. You have an FFT algorithm and increasing the number of points is not a problem. So you take x of n, and in this x of n you have x of 0, x of 1 dot dot dot, x of n minus 1, then pad zeros. Okay, pad the necessary number of zeros to x of n. I'm sorry, after this you pad zeros, 0, 0, 0 up to dot dot zeros. How many number of zeros are you going to pad? This is m point DFT, and how many m minus 1. So these many number of zeros you are going to pad, m minus n number of zeros you must pad. So take this sequence. Okay, instead of taking x of 0 to x of n minus 1, you take from x of 0 right up to m minus 1. Okay, so that's how you will calculate the m point DFT. But given original sequence is n point DFTs. Okay. Any other point I would like to mention here? One second. Okay, right. So you have padded a sufficient number of zeros, and also simplifies the computation, because the zeros multiplied by anything is 0. So if you compute the m point DFT of this sequence, m point DFT of this sequence, that is of this extended sequences, you are extended, right? Extended sequence, then you will get samples at intervals of, instead of 2 pi by n, you will get at the intervals of 2 pi by m. So this is an alternate method for doing this. Either you use interpolation, the first option is interpolation. Okay, if you don't have good computation facility. Okay, and you can go to artificially extend the length of sequence by padding zeros, and then take DFT using FFT algorithm. Okay, if you have good computation facility. Either way can do it. Okay, and here your given sequence is n point, so n point to m point you are calculating, and in this one straight away you calculate n point DFT, and from there you employ interpolation formula. This interpolation formula already I gave you in the last lecture. Okay, so that's how one can compute DFT in either method. Okay, so let me stop at this point. In the next lecture we will move on to the properties of DFT. Okay, so let me stop here.